Now that we have that under our belts, we're now going to look at a tank that's 8 meters long, 4 meters wide, 2 meters high that contains kerosene. We're given the density is 820 kilograms per cubic meter, and that's in kilograms, so we're going to have to bring in 9.8. And the kerosene is it filled up to a depth of 1.5 meters. We're asked for the hydrostatic pressure on the bottom, hydrostatic force on the bottom, and then the hydrostatic force on one end of the tank. Here we have our tank, and our rho is given to be, as I said, 820 kilograms per cubic meter. Now, since this is mass density, we need to consider bringing in gravity, so 9.8 meters per second squared. So in terms of units, rho times gravity is going to be a kilogram per cubic meter times a meter per second squared, and that's a little cumbersome. But remember that a kilogram meter per second squared, or kilogram times gravity, is a Newton. So at this point we have a Newton per cubic meter. We said that pressure is a force per unit area, so it should be Newton per square meter. Now this should make sense. Here we have a kerosene that's a level of kerosene that's 1.5 meters, and it's creating some force on the bottom of the tank, or pressure. If the depth of the kerosene were greater, then we would have an increased amount of pressure. What this is leading to is that pressure is rho times gravity times the depth that we're talking about. And in terms of our units, we already had a Newton per cubic meter. And when we multiply by the depth, which is meters, right, then we end up with a Newton per square meter, and that agrees with what we had expected. So what we're going to have here for part A is that the pressure is rho, given to be 820, times gravity, 9.8, times the depth, which we were told is 1.5 meters. This gives us an answer for pressure of 12,054 pascals, which you may also see written as 1.2054 kilopascals. For part B, as far as the force on the bottom of the tank, force is going to be pressure times area. And so here we've got that the force is equal to the pressure, and we're going to use the 12,054 times the area, and the area is referring to the area on the bottom of the tank. And so 8 times 4, 32. So 12,054 times 32. And so the force is equal to 385,728 newtons. And we end up with newtons by using the pascals, because the pascal was built on the newton, right? Using the kilopascal, we'd end up with like kilonewtons. So those are parts A and B. Those are fairly straightforward. For part C, we want the hydrostatic force on one end of the tank. So we're talking about the force exerted on the side of the tank here. Now, it's really key to consider what we've just done. Force is going to be, well, we said pressure times area, but I want to unpack that. Rho times gravity times depth times area. And as you're considering force in this section, if you can remember rho, gravity, depth, and area, that really is the key. Now what we need to do is we need to consider the area on the side of the tank and the depth on the side of the tank. Here's the thing. At the top, the depth is 0. At the bottom, the depth is 1.5 meters. And the depth will take on values between 0 and 1.5 meters. And so what we're going to do is we're going to consider a strip along the side of the tank. And we're going to say that this strip has a height of delta y. And then we have a couple of choices as to how we can label our quantities here. What I'm going to do is I'm going to label the distance from the bottom of the tank up to that pink strip as y. And then the distance from the top of the tank to that pink strip is going to be 1.5 minus y. By doing this, what we have is that y points in the up direction, like we're used to. We won't always try to do that, but it makes sense in this case to me. So here we can say the incremental force is equal to rho, which is 820, times gravity, 9.8, times the depth. Now the depth is the depth of the pink strip, and that's going to be 1.5 minus y. And then the area of the pink strip. Well, the area of the pink strip is its width, which is delta y, times its length, which is 4. And I'm sure it comes as no surprise that we're going to sum up a bunch of little incremental forces. The result is that the force is going to be the integral of 820 times 9.8 times 1.5 minus y times 4 dy. And we can see that y will go from 0 to 1.5. Simplifying and computing this integral will give us 36,162 newtons for the force. We could also write that as about 3.6 times 10 to the 4th newtons. And I said about, so I should probably use a squiggly equal there. And that's going to be our answer. Take your pick. You can either give it in scientific notation or not.